The infinite universe hypothesis proposes that the universe is neither finite nor bounded, but instead extends infinitely in all directions. It's a concept that challenges our intuition and forces us to confront the truly awe-inspiring nature of the cosmos. To understand the infinite universe hypothesis, we must first grapple with the concept of infinity itself. Infinity is not just a very large number. It's a concept that transcends our everyday experience. It means without end, without limit, a concept that's both fascinating and daunting. Think of a number line. It stretches infinitely in both directions, with no beginning and no end. Similarly, the infinite universe hypothesis suggests that space itself could be like this number line, extending forever in all directions. This means that no matter how far you travel, no matter how many billions of light years you traverse, there would always be more universe to explore. If the universe is infinite, does that mean that everything that can happen will happen? Are there other versions of ourselves out there living out different lives in distant galaxies? One of the most compelling pieces of evidence for an infinite universe comes from the study of the cosmic microwave background, or CMB. This faint afterglow of the Big Bang permeates all of space and provides a snapshot of the universe as it was just 380,000 years after its birth. The CMB is remarkably uniform, with almost the same temperature in every direction we look. This uniformity presents a puzzle. If the universe were finite, we would expect to see variations in the CMB temperature, reflecting the different conditions that existed in different parts of the early universe. However, the observed uniformity suggests that the universe was incredibly homogeneous in its infancy, which is consistent with the idea of an infinite, unbounded cosmos. The CMB also contains tiny fluctuations in temperature, representing the seeds of the galaxies and stars we see today. These fluctuations have been analyzed in great detail, and their statistical properties provide further support for an infinite universe. The patterns observed in the CMB are consistent with a universe that is either infinite or much larger than the observable universe. The distribution of matter in the universe also provides clues about its size and shape. Observations of galaxies and galaxy clusters reveal a remarkably uniform distribution on the largest scales. This means that no matter where we look in the universe, we see roughly the same density of galaxies. This large-scale uniformity is difficult to explain in a finite universe. If the universe were finite, we would expect to see a gradual decrease in the density of galaxies as we look farther away from our own galaxy. This is because the light from distant galaxies would have had less time to reach us since the Big Bang. However, observations show that the density of galaxies remains relatively constant out to the limits of our observation. This suggests that the universe extends far beyond what we can see and further supports the idea of an infinite cosmos. This uniformity, stretching out billions of light years, implies a continuation of this structure beyond our current limits of observation. Another crucial piece of evidence comes from measurements of the universe's geometry. According to Einstein's theory of general relativity, the geometry of the universe is determined by the density of matter and energy it contains. A high density would result in a closed universe shaped like a sphere, where parallel lines eventually converge. A low density would lead to an open universe shaped like a saddle, where parallel lines diverge. A universe with a specific critical density would be flat, with parallel lines remaining parallel forever. Measurements of the cosmic microwave background and the distribution of galaxies indicate that the universe's density is remarkably close to the critical density, suggesting that the universe is either flat or very close to flat. A flat universe is consistent with an infinite universe, while a closed universe would be finite. The expansion of the universe is another factor to consider when exploring the possibility of an infinite universe. The observation that galaxies are moving away from each other, with distant galaxies receding faster than nearby ones, suggests that the universe is expanding. This expansion does not mean that the universe is expanding into something else. Instead, it means that the space between galaxies is stretching, causing them to move apart. If the universe is infinite, this expansion would simply continue forever, with no end in sight. The rate of expansion is governed by the universe's contents, including dark matter and dark energy. Understanding the nature of these mysterious components is crucial for determining the ultimate fate of the universe and whether its expansion will continue indefinitely. However, the current understanding of the universe's expansion supports the possibility of an infinite cosmos, constantly stretching and evolving. If space is truly infinite, then every possible arrangement of matter, every possible combination of particles, must exist somewhere. This means that somewhere out there could be regions of space that are remarkably similar to our own, perhaps even containing planets like Earth and civilizations like ours. This concept of cosmic doppelgangers is a mind-boggling consequence of infinity, suggesting that our own existence, while precious, might not be entirely unique in the grand scheme of an infinite cosmos. The notion of an infinite universe, while awe-inspiring, leads to some truly perplexing theoretical implications. One of the most fascinating is the concept of cosmic doppelgangers. If the universe is truly infinite and the laws of physics are uniform throughout, then the arrangement of matter must repeat at some point. With an infinite amount of space to arrange matter, the same configurations of particles, stars, galaxies, and even planets must reoccur. This means that somewhere out there, billions of light years away, there could be an exact copy of our solar system, with an identical Earth inhabited by our cosmic twins. Even further out, there could be another copy, and another, and so on, infinitely repeating across the vast cosmic canvas. The concept of infinity throws a fascinating curveball into our understanding of probability. In a finite system, we can calculate the likelihood of an event occurring based on the limited number of possibilities. However, when we introduce infinity into the equation, the rules change dramatically. In an infinite universe, any event, no matter how improbable, becomes not only possible, but inevitable. Given enough opportunities, even the most unlikely event will occur, simply because infinity provides an endless number of tries. This means that everything that can happen will happen an infinite number of times. This has profound implications for our understanding of life itself. If the conditions that allowed life to arise on Earth are possible, then in an infinite universe, those conditions must be met an infinite number of times. This suggests that life, far from being a cosmic fluke, could be a common occurrence scattered throughout the vastness of an infinite cosmos. Despite the compelling evidence supporting the infinite universe hypothesis, directly proving infinity remains an elusive goal. Our observations are limited by the observable universe, the portion of the cosmos we can currently see from Earth. This limit is determined by the speed of light and the age of the universe. We can only see objects whose light has had time to reach us since the Big Bang. This means that even if the universe is finite and curved, it could be so vast that it appears flat within our observable universe, much like a small section of a large sphere appears flat. This inherent limitation makes it incredibly challenging to definitively prove or disprove the infinite universe hypothesis through direct observation. While directly observing infinity might be beyond our current capabilities, scientists are constantly exploring new ways to probe the universe's structure and test the infinite universe hypothesis. Future observations and experiments could provide more definitive answers, refining our understanding of the cosmos's true nature. One promising avenue is the study of the cosmic neutrino background. Neutrinos, ghostly particles that interact weakly with matter, were produced in abundance in the early universe. Detecting these primordial neutrinos could offer a glimpse into the universe's state even earlier than the CMB, potentially revealing clues about its overall geometry. Another approach involves searching for subtle patterns in the cosmic microwave background that could indicate a finite universe. If the universe were finite and closed, light could theoretically circumnavigate it, creating faint repeating patterns in the CMB. Detecting such patterns would provide strong evidence against an infinite universe. Further advancements in telescope technology, such as the development of even more powerful space telescopes, could extend our observational reach, allowing us to map the distribution of galaxies and galaxy clusters over even larger distances. This could reveal subtle variations in density or structure that might hint at the universe's true size and shape. The possibility of an infinite universe raises profound philosophical questions about our place within it. If space extends endlessly, filled with perhaps infinite variations of matter and energy, what does that mean for our own significance? Does our existence, confined to this tiny planet orbiting an average star, become meaningless in the face of such immensity? Some might find the idea of an infinite universe daunting, even depressing. The sheer scale of such a cosmos can make our everyday concerns seem trivial. Our individual lives a fleeting flicker in the grand scheme of things. Yet others find solace and wonder in the idea that we are part of something much larger than ourselves. The concept of infinity challenges us to reconsider our definitions of significance. Whether the universe is truly infinite or simply unimaginably vast, the implications are profound. The possibility of cosmic doppelgangers, the inevitability of every possible event, the sheer scale of existence, these concepts challenge our assumptions about reality, urging us to embrace the humbling yet awe-inspiring nature of the cosmos. The quest to understand the universe's true nature is a journey without end, a journey that takes us to the very edge of knowledge and beyond. Whether the universe is infinite or finite, bounded or unbounded, one thing remains certain. It is a universe filled with wonder, mystery, and endless possibilities for exploration and discovery.